very happy that he is here again. Gerrit Grunwald from Azul, and he will now give us some trash talk, and I really wonder what's that all about. I wish you everybody a lot of fun. Gerrit, it's your turn.
Okay. So just as an info, it was 176 slides. Now it's just 150. So, and the original slide deck was 270. So we will make it. Maybe an hour if everything works out. Yeah, so welcome to the session about garbage collection. Do we have any garbage collection experts here? If yes, then you can go, right? And then it's done. So this is not a deep dive into garbage collection. First of all, that's too boring. Second, it's way too complex for a session. This is more a little overview. My name is Gerrit Grunwald. I'm working for Azul, as you can see. And yeah, that should be it. Memory management. Who's a Java developer here in the room? All right. Okay. Who's not a Java developer in the room? What else? Okay. Okay. But the principles will be more or less the same, so it should be very similar to. They have garbage collection, right? So memory management in the JVM is automatic, right? So who's setting here a garbage collector explicitly in production? 1, 2, 3, 4, sometimes. But usually you just take the default, which is fine. It's not a problem. So why care at all, right? Because it seems to work. Well, it has an impact on application performance, responsiveness, and resource usage. So system requirements like memory and CPU, right? So these are the 3 reasons why you should at least have an idea what it is and how it works. Because sometimes you run into strange problems. Usually you don't have to take care about garbage collection, but if something goes wrong, then it's good to know how it works, because usually typically it's the garbage collector. There are 2 scenarios. First is, you have some problem, put more CPU on it, right? That's the first thing. Oh, it didn't work. Add more memory, also didn't work. Okay, this is garbage collection problem, right? Usually this is the scenario. And then it's good to know how it works. Just as a reminder, how it works in the JVM. So every thread has a stack, and on that stack we put so-called stack frames. And for each method in that thread, there will be a stack frame that will be put on this stack, right? And this is growing and shrinking dynamically, and it is locally accessible as it's thread safe. That's no problem. And usually, if you leave the method, the stack frame will be put from the stack, and that's it. Okay. And then we have the heap. And we saw before, in the heap is the place where all the objects live, right? The actual implementation, because here we only have primitives and references on the stack. So in the heap is shared access. It's not thread safe, and there we need to do garbage collection, right? It happens here, not here. But this is an essential part of the whole process. And then we have the metaspace, where we don't want to look into that today. It contains class metadata, constant pools, and other stuff. You can say it's simply everything the JVM needs to work with classes. This is in the metaspace. So not really important for this session, so we skip this part, because this is mainly happening here. Okay, to give you an idea how it works, I wrote some code. I hope it's readable from the back. Pretty simple. I have a record, person. I have 4 instances. I have a list where I put the instances in there. I print out P1, my name, that's it. Easy. The stack for thread 1, which is here for this main method, this is all simplified, right? Would probably look similar like this. So we have the references for the person objects and for the list on the stack frame. And then in the heap, we have the objects. And then we have references that pointing from the stack into the heap to the objects, right? And that's a very essential part of the whole process, because later on, this is always named the roots for garbage collection, right? So garbage collection starts here in the stack frames at these references. Okay, so that means at the moment, all of these objects are reachable. We can reach them from the stack into the heap. because all references are there. So now I set P1 to null, okay? Means the reference is gone. That points to the P1 object. But if I would now print out P1, it will say null, but it's still there, right? Because there's an internal reference from the list object in the heap, points to the same object. So if I put something on like, did I put it there? No, it's the next one. So it's still reachable via the list. So I can do something like this. System of print line persons get 0, and it will print out the name because the object is still there. If I set the list now to null, the reference to the list is gone, and then only these 3 objects are reachable, right, from the stack. That means the rest is garbage. It's lying around. It still consumes the space and memory, so we can't allocate new memory there because they are still objects. And how to get rid of this stuff? Garbage collection, right? This is the main idea behind it. So just shortly what it is, form of automatic memory management. There's also automatic reference counting, or if you do it manually in C, then you have to do the malloc-free stuff. But in principle, there's no better or worse. It's both good and works, and both have their flaws. But if you do garbage collection or reference counting, it's no problem. For example, Swift uses automatic reference counting, and it's no problem at all. It identifies and reclaims no longer used memory and ensures efficient memory utilization. The most important part is this one. It frees you from doing this stuff manual. Right? This is the main idea behind it. Some C programmers here, they love the malloc and free. It's, yeah. Okay. Who knows what stop the world is? Yeah, some, and which is fine. You don't have to, but it's good to know what it is, because 10 years ago this was one big topic, right? Stop the world was one of the problems in the JVM. To give you an idea, you will now see some application threads running, right? This is your application, and then we have to do garbage collection. The JVM sends a so-called save point signal to these threads, and that means all of the threads will be put into a so-called safe state. And this is then we reach the JVM save point. That means all threads are stopped, application threads, and then all threads in the safe place. So we are at the JVM save point. And what now happens is now we can do a garbage collection here with one or multiple threads, because no application thread is going to the memory at the moment. Once we're done, we just continue with the application threads, all right? This pause, the orange area, depending on the garbage collector, can take up to seconds. Like 10 seconds. It's very worst case, but it can happen. Means if you have a REST endpoint, for example, and then you have Black Friday, right? And someone's trying to buy something, then suddenly nothing happens. It looks like the machine is stuck, but it's really just garbage collection going on. So nothing works on the JVM, right? So you can't really see anything. And the online shop is a nice example. If you have a high-speed trading application where you make millions in milliseconds, you can imagine if it sits there for 10 seconds, then you lose a lot of money in the worst case, right? So it was really a big problem and still could be. So, but this is, if I say STW or stop the world, then this is the space and time that we talk about. Now let's take a look about collectors, and this also applies for C# and other languages, because we talk about the basic principles. Who knows mark and sweep or heard about it? Probably in the university. It's a so-called non-moving collector, the most simplest collector principle that it's out there. So this should be the heap, very, very simplified. In my example, one memory cell is exactly one object, right? Which is not the case in reality. So you will now see the gray ones is the free memory, the blue is the allocated memory. If it's purple, it's dead, so no reference is pointing to this object anymore. If it has this little red square on the upper left, then it's marked. That means the garbage collector can reach it. It's live. And then if it has a number in there, it means we do a garbage collection, everything that's dead we remove, and the stuff that survived, right, we increase the counter. It's like a survival counter, right? So now let's start the demo. You will see we allocate memory. You see objects die quite fast, which is not really surprising. And once the heap is full, we stop the world, we mark all the live objects, and then we remove the rest. So now stop the world, mark, remove, continue, right? And you see already the problem. Who knows Windows 3.11? Disk defragmentation. That's the magic words. And this is exactly the same. Happens on the heap, right? If you do this. Because you see, we don't move objects. We just kill the dead ones, remove them, and then we try to find new places for the new objects. And this is exactly the problem, not with this one, but if you have objects that are larger than one memory cell, you need maybe continuous space. And it gets harder and harder to find that, right? Because the heap gets cluttered more and more. Which the advantage is you don't have to move stuff around. The disadvantage is, yeah, it's fragmentation, right? Big problem here. But still, not a bad garbage collector. It works. One thing I didn't mention here because I stripped down slides, I would like to mention now. The freeing step is indeed not very performant in this kind of collectors, because what they have to do, we stop the world, we find all the live cells, and now we know all the stuff that has the red square on it is live, and all the stuff that is purple is dead. So we can remove it, right? But it's not that easy because we don't know where is this stuff, because there are no references in the heap. That means we have to go through each memory cell and check. Is this live? Oh no, it's free. Is this live? Yes. Oh, this is purple. Oh, I can remove it. That means the bigger the heap with this collector, the longer it takes. The freeing, just the freeing, right? Just keep that in mind because freeing is not for free. Next one, moving collectors. We have two different principles here. And I only talk about precise collectors. There's also something called conservative collectors, but we don't talk about that because they are not in the JVM. We have two different ones. We have the compacting collector and we have a copy collector. First, compacting, mark and compact. And this one is, in fact, in use in the JVM. Pretty much the same, but instead of removing just the dead objects, we add an additional step and compact everything, in this case to the upper left, right? This is just to give you an idea. You will see, when I stop the world, I will stop it here. I will leave some space at the end for free, or leave it free. And the reason for that is when you stop the world and you mark everything and you remove it and you would like to compact, right? In this collector, no problem. If you have bigger objects, you need to copy them somewhere before you can free space, right? You need some headroom to copy objects before you can compact it. And that's the reason why we have to keep some space at the end. And this could be quite big, depending on the size of the heap. And again, now it will stop when we reach the second last column now. Stop, mark, remove, compact. Continue, right? The biggest advantage now is we can just allocate memory very fast because everything's free in front of us. And fast memory allocation means fast application. You would like to have as fast memory allocation as possible. And this is a problem with some collectors because, especially with the first one, they get into, we talk about memory pressure here. So if you have an application that allocates memory as crazy, right? The garbage collector can't keep up. And this is so-called the allocation stall. This can happen with the other collector. If you have something like this, it's great because it can just take memory all the time, no problem, right? But then we have the stop the world pause, which is, again, another problem. But you see the advantage here, right? So we have always free space ahead. It's cool. Problem is, when we do compact, we move objects in the heap. Remember the references that point to the objects. We have to update all the references too, right? So it's an additional step, not only copy, but also update references, which is very important. Otherwise, the reference would point to a different space where maybe no object is anymore, right? So this is very important. Headroom could be up to 50%. That really depends on the heap size. It means then, in fact, you might only end up with a half of the heap that you can use. Now the next one, copy collector. This is different, and you will see why. Now we have two spaces, and they have the name to and from space. Some collectors name it survivor space 1, survivor space 2, but this is a different one. Here it's the to and from space. We will start allocating memory in the to space here on the orange one. Once this is full, we mark all the live objects and copy the live objects into the to space. They will toggle when we stop the world, right? So you will see when I run the demo that this one will be gray and this one will be orange after the stop. And we copy everything over. And if you remember, if I copy into an empty space, it's directly compacted, right? First advantage. Second advantage, if I copy all the live objects to the new space, I know that the rest in this one is garbage. I can directly remove everything. I don't have to check every memory cell, right? So these are two advantages with the copy collector. So you already see the disadvantage here. We need 2 times the space, right? But this is one disadvantage. So now we stop the world. Now toggle, mark, copy, clean up. And it's already compacted on that side. And now we do the same, vice versa, and so on and so on. So this goes on and on all the time, which is pretty interesting because it looks simple and it can help a lot, but it has also another problem here. And now this leads me to these numbers. If you have objects in your application that live for the whole lifespan of your application, that means you have to copy them every time, back and forth, updating references all the time. Even if you know that the object will never be killed, right? No, you have to copy it, right? And if you have big objects, means takes time. So this is the disadvantage. Long-living objects, you have to copy all the time, and you need twice as much memory as with the other collectors. But you have more speed because you can free up faster, and you can always compact by the copy step, right? Okay, so these are the 3 basic principles that you need to know. So it's not that much. And that leads me to generational collection. Does everybody know what that means? Probably not everyone. We will talk about generational mark and compact. And it's pretty simple. You have to know that the weak generational hypothesis, most objects die young. And the reason for that is pretty clear. Because it's a good practice to write a lot of methods, right? Small methods. So that means every time you call a method, you get a stack frame on the stack. When you return from the method, stack frame will be removed. That means the references will be removed. You create garbage. Lots of small methods means lots of garbage, okay? That means this is why the chart looks like this. This is the number of objects, this is the lifespan of the object, or lifetime. You see we have lots of objects that die very quickly. Then we have some objects that live a little bit longer, and then just a few that really live for a long time. That means we can talk about some kind of generations here. And now if we take the principles that I explained to you and try to use them to shape for this behavior that we know, then we can do something like that. We create a so-called Eden space. Eden because we create objects only here in this yellow one, right? And this can be small because objects die young. That means we can do lots of garbage collection in this small space because that is fast, right? Because even freeing is fast in this one. And then we use, in the next one, we use a copy collector here. And this is where you see the survivor spaces. And the reason is, that's the next step. I told you the problem with the copy collector is you have to copy objects all the time, even if they last forever. Now we have a threshold. If I copy them, let's say 15 times, we just take the object and promote it into the Ternert space, which is the old generation here, right? This is the idea, to get rid of old objects where we know, well, they will live forever. And this is the so-called young generation. So that means we have, I always have to check because my computer is one step behind this screen. This is the young generation, the yellow, and the copy collector here. And this is the old generation, stuff that lives for a long time. And we can do different garbage collections here, because I told you in the yellow one we do all the time garbage collection. Then sometimes we do it here, and this is very rare, right? So that means we have the minor collection here, the major collection there, and we have a full collection if we do both collections here and there, young and old generation. Okay. Nice to take a look at it. better is to see how it works. Again, we will allocate only in the yellow. If it's full, we stop the world, we copy the live objects into the to space, continue. Again, full, copy the live there. If this is full, we flip, copy the live objects here, toggle and so on. And then if they, in this demo, if they survive 3 times the garbage collection, I promote them into the old generation. That's the idea. And we will do that once, and then I will do fast forward. And you will see some kind of wave moving through this space. Because even here objects die, right? So that means in the end, more or less, only on the right side we have old objects, they're still alive, and the rest is all dead. Now let's take a look at it. So, we allocate, objects die, stop the world, mark, copy, first toggle, then copy, continue. Allocate here, still objects dying, and then mark, copy, toggle, copy the stuff over, and so on. So this is the process. And like I said, if we reach 3 times, at the 4th time, they will be promoted to now. And now you see, now it will be faster. And now you see how like a wavefront, this is when people talk about a wavefront, they mean this. It's moving through the old generation. And if the old generation fills up, we do a full collection here. So we stop the world, we mark in this area the live objects in the old generation, compact it, and then we copy everything that's still live in the young generation to the old one. Let's take a look at it. Mark, compact, copy everything over, and continue. This is how this generational collection works in principle. And then you see this, why this is called survivor spaces, right? So it's survivor space 1, survivor space 2. This is how it's called in the CMS garbage collector, where we will talk about later. But you get the principle, how it works. Okay. With this one, we can pretty much adapt to the behavior of object lifecycle, which is quite good. The problem is the old generation usually is quite big. And if we have to do a garbage collection in this one, it takes long, because this one is, we have to check for freeing all the memory cells, right? This is mark and compact in this collector. Okay, so now you know generational collection. Like I said, very basic principles. This was all serial, means we stop the world, we do our stuff, continue. Now there's concurrent collection. That means we allocate memory, and at the same time, we clean up the heap, right? Garbage concurrency is hard, right? Let's take a look how you can do concurrent marking. I didn't went into details how the marking stuff works, but marking is the garbage collector follows from the stack frame into the heap, finds an object, reach it, mark it as live. It's flipping a bit, and then it goes from there to the next one, and so on. This is the marking phase. If you would like to do that at the same time where the allocator is allocating memory, can be tricky. So we start from the stack frames, which are squares, and the garbage collector just starts, find the first reference, reach it, and I use different colors here because you will find it as a 3-colored marking process. This is usually used in a garbage collection language. So we reach it first, we mark it live, we go to the next reference, right? So now suddenly, because we are concurrent, the application thread decides, you know what, this reference I don't need anymore, but I establish a new one, this one. The garbage collector passed already this cell, so he doesn't know about this. So he goes on, marks all the cells that he can find. This one he can't find because they point in this direction, so this is more or less dead. And then in the end, it won't find this one, so it will crash. How can we overcome this problem? It's not so easy, but there is something called barriers. Did someone heard about barriers? It's a pretty simple principle. We have read and write barriers, and this you can think about some piece of code that is installed on each memory cell, right? And once you would try to read it or write it, depending on what kind of barrier you implemented, there is some piece of code that has to be executed first. So that means I would like to read this memory cell. Yes, execute the code first. Okay, now you can. This is how it works. So it's additional code that will be executed. This is no Java code. This is assembly code. And we talk about something like 2 CPU instructions, something like this. Very small, very efficient. So like I said, it's code that will be executed either when writing or reading a memory cell, or both. Can be both. This is used, for example, we didn't go into that one because of time, but I told you we have the young generation and we have the old generation, right? And we have different garbage collectors here. Minor collection, major collection. What about references that pointing from the old generation into the young one? That means from the blue area into the yellow one, right? Could be possible. And now I do a collection in the yellow area. That means there is no stack frame that I can follow that comes from the blue area into this yellow one, because I do only a collection in the yellow one. I need some kind of mechanism to figure out that, yes, there is a live cell here, but the reference is coming from the old generation, and I don't do a garbage collection in the old generation. So for this kind of stuff, there's a so-called card table or remembered set. The JVM knows that, of course, and tells the garbage collector, yeah, there is some reference coming from the old generation. For this kind of stuff, you need barriers. Also, to synchronize between the allocator that allocates memory and the collector that cleans it up. So for these mechanisms, you need barriers. One thing you should keep in mind, when you read memory, you have an application, and usually we have 75% reads and 25% writes. This is just an average for programs. That means if you only do a read barrier, then it will be triggered 75% of the runtime. This will be triggered, right? That means it has to be very efficient to do that. Like I said, we have Azul as a garbage collector that only does 2 CPU instructions to do that. Otherwise, it's not possible because it will bring down performance. All right. If we use a write barrier in this example, same thing as before. Garbage collector starts following references. Here's a write barrier. So because it's just reading, no problem. Again, and now the application thread steps in, it triggers this write barrier, right? Because it writes something. It takes this one way and creates a new reference there. And in this example, I just tell the JVM, if you remove a reference, then mark this cell where it was pointing to as reachable. Not live, just reachable, the gray color. So garbage collector is already here. We have the new reference here. This is the write barrier code. It marks this cell, but not as only reachable, not live. Garbage collector continues doing his job once it's finished, and now this is the new stuff. In this case, we do a remarking phase. The garbage collector, because there's one cell which is just still reachable, it goes again through the references and it will find this one because of this reference. If it wouldn't be here, right? If this was just removed, then it will just clean up this cell. But in this case, it will find it, it will mark it and say, okay, there's another one live, and then it can do the garbage collection. And then it will do a stop the world, right? Even if it's concurrent. We have stop the world pauses, even in concurrent collectors, but they are so small that people just don't talk about it. We talk about it's below milliseconds. It's really short breaks where we have to do something like that. Atomic operations in the JVM. Okay, this is how a write barrier can work. It's quite complex, so I try to explain it that you get an idea. You just have to keep in mind there are barriers that can help you with this concurrent garbage collection stuff. Another thing, if you do concurrent copying, that's quite interesting. Remember, we do, for example, compacting the heap. We copy an object to a new location, right? And now we do that concurrently. At the same time, when the application is allocating new memory, we move stuff around, right? And you can imagine that can be quite tricky. So this is the old position in the heap, and we would like to copy it on the other side. We do it, first of all, stop the world. So we stop the world first. Nothing happens. Now we can copy the object, no problem. Then we install a forwarding pointer here in the old object, and that one points to the new one. And then we update all the references, because here's a pointer that points to the new object. Once we updated all the references to the new object, we can remove the stop the world and then continue, right? This is stop the world. Easy peasy, no problem. Now we can remove this one and everything points to the new one. Okay. If we do that concurrently, then it would look like this. We start, same thing. We copy the object and we install the forwarding pointer. We start updating references. Both objects now are live on the heap, right? That means if now threads access this one, this object, it can go directly here and the other one can go to this one. This is possible, right? That's the worst thing that can happen. There's a trick to overcome this problem, and it's a so-called Brooks pointer that you can use. This is used in Shenandoah. It's one of the collectors. What they do is, directly when they create an object, they install a forwarding pointer on top of the header, and it points to the same object header. Doesn't make sense at all if you see it like this, right? But if you copy now this object to the new location, the pointer points to this one. And at this moment, it's totally dead. No one can see it. And now the trick is that they use is now coming, because what they do is they move this forwarding pointer to this header. Right? This is an atomic operation. Nobody can step in. This is like below 1 millisecond. It's really just pointed to the new location. And then they start updating references here. Because at the moment, everything's still pointing to that one. Fine. But then when you point to this object, you can update things. Objects will find this one if they follow this stack frames. And others will use the old one and will be forwarded to the new object location, right? And with this, you can do concurrent copying in the heap. Once you updated all the references, then you can remove that. I explicitly tell you this because, remember, if you copy things around, you always have to update all the references before you can remove the old object position, right? That means you need more space if you copy stuff, because you have to keep old objects in their location until you updated all the references. Okay? Good. And then you can continue. Fine. This is the principles. Everybody still with me? Okay, that's good. It's quite complicated. Serial collector. It's the oldest one in the JVM. To make it simple, everything is on one page. You will find some information on this one. I will probably provide the slides afterwards. Yes. So then you can look it up on your own. Then we don't have to read through all of that. The serial collector is a little bit special because, especially these days, it was, like I said, the first one in the JVM. It was made for small machines, and if you read something like heap size small medium, pause times longer, there's a reason why I keep it this fluffy. Because when they invented that, small meant, I don't know, a few kilobytes, maybe? Today, small can mean 2 gigabytes. You never know, right? So this small, you get the idea. It's 2 gigabytes, below 2 gigabytes, maybe half a gigabyte. But it's not terabytes or 64 gigabytes or something, right? This is small to medium. Longer means probably seconds, right? Can be. Okay. The special thing with this collector is, and why it's interesting today, why I spent more time on that one than on the others, who's working with microservices here? Who's working with small microservices? Who has to decrease the memory size because it's so expensive, right? You have to keep it down. And then you run into this problem because this collector has two specific things. If you work just with one CPU on your node in your cluster, or if you have less than 1.8 gigabytes and you don't define a garbage collector, you will get this one, if you like it or not. And this is tricky because usually people assume, oh yeah, I get G1, that's easy. If you have 2 gigabytes, you get G1. If you have 1.5 gigabytes, you don't get G1, you get this one. That means suddenly you might see garbage collection pauses that you didn't see before. And especially these days, if companies try to reduce cloud costs, right? So that, can we somehow make it smaller? Why do we need 2 gigabytes of RAM for each node? Can we make it smaller? Sure, you make it smaller and suddenly someone reports, we have these strange effects. Sometimes the service is stuck. I don't know what it is. And then it continues working. But this is one of the problems. So it's always a good idea to set specifically a garbage collector if you work with smaller nodes. Because what happens with the serial one is we have all the application threads, then we have stop the word, and then we have one thread that does the garbage collection for the young generation, the yellow and the copy collector. And then for the old generation, the same, just one thread doing that. That means even if you have just 2 gigabytes or 1.5 gigabytes, it might take some time to clean up the heap, right? Okay, keep that in mind. So the serial one is very specific because this will be taken. And the reason for that is also quite interesting. It's because at that time when it was invented, people couldn't imagine that a machine that has just one CPU never will be a server. Right? That's for sure. And if it has less than 1.8 gigabytes, it's not a server. That's pretty sure. That's the reason why it's implemented like that. Okay, then we have the parallel collector, and we will go through that now a little bit faster. Pretty much the same, and it's called the throughput collector for a reason. Throughput means the time that we spend in the application versus the time that we spend in the garbage collection, right? The more time we spend in the application and the less we spend in the garbage collector, the better, right? The higher throughput. So, I won't go into details here. Let's take a look at this one, because this is a little bit different. You see, we have now multiple threads that can do garbage collection in the young generation. Young generation was the yellow part. And the copy collector. That means very often it can take up to all the available threads. That makes it so fast, right? Because it stops the word, then it does quickly the garbage collection with all the threads, and then it continues working. But if you run out of old generation, there's only one thread. Again, can lead to seconds of garbage collection pauses, depending on the size of the heap. But yeah, that can be tricky. If you don't run into this problem that you have to do a major collection, then it's fine. But if you have a major collection with a parallel one, can be slow. But this was the default garbage collector from JDK 5 till JDK 8. That means even in JDK 8, this is the default. It's not G1. That came with JDK 9. But you could use it already in JDK 8, right? You can switch it on. There is this, there in the lower right part, you always find the switches, how to switch them on. All right, so this is parallel. How are we on time? Oh, okay. CMS, concurrent mark and sweep. This collector looked pretty much the same like I showed you the generational version. So with Eden, the survivor spaces, and the tenant space. So this is more or less how it looked like. It's deprecated. It's not even in the JVM anymore. So that was removed in JDK 14. It was invented in JDK 1.4, and the main reason was we had to find a way to predict garbage collection pauses, because it's really critical if you run mission critical stuff and you never know, how long will it take? A second, 10 seconds? When will it happen? You have no idea. So this collector guaranteed max 1 second garbage collection pause. That's good, because now you can plan, right? Because you know, okay, my application will at max stop for 1 second. That's the worst case, but it will probably be better. But the problem here was that it didn't compact the old generation. That means it was mark and sweep. And you end up with a completely cluttered heap. And that was the problem with this collector. So this is one of the reasons why they removed it. And there are also other reasons. The code was super complex because it was already partially concurrent. It can do concurrent marking and stuff. But I think nobody was really keen on continuing supporting it. That's the reason why they deprecated it. You see the diagrams will be more and more complex, so we won't go through this stuff. It was deprecated in JDK 9 and removed from JDK 14, so if you're in 15 above, then you won't even be able to switch it on. It's not there. It was completely removed. This leads me to this one, which is a very nice one, G1. Probably everybody knows that, right? This is the default collector these days. And it looks like this. It looks different from the others. This is a region-based collector. Remember, we had this Eden, survivor spaces, and so on. This now has regions, and the regions are, the size of the regions depends on your heap size that you define with minus XMX. So it can be up to 32 megabytes. This is the biggest size a region can be. This is already one of the advantages, because 32 megabytes, a garbage collection in 32 megabytes, even this is fast, right? Because this is a small area. Remember, the old collectors, there could be region sizes of gigabytes, right? So that means if you do the full collection in a gigabyte, it takes forever. Here, the approach is different. If it works, during its working, it looks something like that. You will see we still have Eden regions, we have survivor regions, and we have tenert regions here, the blue ones, and we have humongous regions. Humongous regions are huge. Now, they are just a little bit more than half of a region size. If you have an object that is a little bit bigger than half the region size, it will directly become a humongous region. Humongous regions won't be moved, so they just stay there. It's like the old generation, like the blue ones, because they're expensive to move. And the problem with these ones is, I know we had some customers that have exactly this problem. They have enough heap defined, but they worked with lots of big objects. And their objects always have been a little bit bigger than half of the region size. So they run out of memory, even with a big heap. And they had no idea why, because they said, we don't get it. The reason is, even if it's just a little bit more than half of it, it will give you the whole region, and the rest stays empty. So you lose empty memory that can't be used anymore, and that can lead to problems. There are some use cases where that can happen. Depends on the object size, the heap size, and so on. Usually it helps to just define a little bit different heap size, and then it's good. Okay, let's take a look at it. Of course, I did a demo for that one. We allocate in 6 Eden regions here, and there's a reason why it's called garbage first. We take, once the 6 Eden regions are fully collected or allocated, we take the 2 with the most garbage that happened right now, and then take all the live objects and put them into survivor regions. And then we do the same with the survivor regions. So I use, I think, 3 survivor regions. If they're full, I take the 2 with the most garbage and put the surviving memory cells into a tenert region. Why do I put the ones with the most garbage? Why I take these 2 first? Because they contain the least amount of live memory cells. So copy is fast, right? I don't have to copy lots of stuff because most of the stuff is garbage. That's why it's garbage first. That's the idea. And then you see it goes on, and then once like this, the area is completely dead, so it can just be removed. And areas or regions don't have to stick to a specific type. So the collector and allocator can just use whatever they like. And you see this is a big advantage because that's very flexible, can be very fast, because you always take just a couple of regions and take only the garbage first ones and copy the surviving objects into new regions. Okay, that goes on forever. Yes, this is the, let's say, the best standard collector that we have at the moment, and it more or less guarantees to around 200 milliseconds is the max garbage collection pause, which is quite fast. Usually it's faster. It can be down to 100 milliseconds. It can be down to 50. Below 50 milliseconds, not really predictable anymore. There's one thing you have to keep in mind. It has a sweet spot, which is around 16 gigabytes. This is the heap size where it really has the best performance. Between 16 and 32, it's great. Below 16, it works, but it could be faster. And above 32, also not the fastest one, right? Is someone handling here heaps bigger than 32 gigabytes? Okay, because this is quite rare these days. Okay, you see, I didn't really explicitly talk about it, but the CPU overhead increased here from 5 to 10 to 5 to 15%. The reason for that is it's partially concurrent. And this is something you have to keep in mind. That's very important. As soon as you start with concurrent garbage collection, That means you have 100 threads for your application. You use the parallel GC. That means you have 100 threads for your application, 100 threads for garbage collection, 100 threads for application. If you use a concurrent collector, that means you maybe have 80 for your application and 20 are always used for the garbage collection, right? So you lose CPU performance, or let's say you lose performance if you use a concurrent garbage collector. There was a study from Netflix, of course Netflix. They gave us microservices and now they switched to ZGC, which is a fully concurrent garbage collector. And they only saw a drop of 3% in performance. Well, that's awesome. Well, you have to keep in mind that Netflix is huge, the machines are gigantic, and they have huge heaps, and of course, then you see a drop in 3%. Let me give you one extreme example. You work with a microservice on a node where you have 2 CPU cores. If you use ZGC, it takes 1 core for garbage collection. That leaves you with 1 core for your application. 50% drop in performance. That's what it means. It really depends on your setup. So don't just do it because Netflix told you, oh, we just lose 3%. It's very important to keep that in mind. Concurrency means you have a drop in performance. Okay, this is the diagram. We don't get to this one. It's a default collector from JDK 9 onwards. It can do concurrent marking, also concurrent sweeping. That means cleanup. So this is a quite good collector, and there's a good reason why this is the default. Who knows epsilon? 1, 2, 3, a couple of people. Because this is that's my favorite collector. It's the no collector collector. It's not a garbage collector that you can select, right? You can select the epsilon collector, but you have to also switch on the unlock experimental VM options because there is a reason for that. If you don't have garbage collection, you have no problems, right? Except you run out of memory, like this, because this is just no garbage collection. That means as soon as the memory is taken, it will crash. It was mainly made for testing purposes, right? If you would like to test your application performance without the garbage collector stepping in because you can't really calculate when it will happen, this is the way to go. But there are some smart companies, they use this garbage collector for production because they have also collections where they reuse objects. So their strategy is we don't produce garbage, so we don't need a garbage collector. And that means this is the fastest available code you can write if you don't use garbage collection, but it's also terrible code if you look at it. It looks really terrible because you have to tweak Java in a way that it was not meant to be to make it work. But then if you use it, you can really get the last drop latency improvements or throughput improvements with this collector. But be careful. Who knows, what is the name of it? This tool to monitor the JVM. I don't remember the name. No, older one. Visual VM, exactly. If you use Visual VM, then you can monitor the garbage collection, right? The memory usage. If you use this collector, do yourself a favor and run it with Visual VM. Because sometimes if you start it, you press start, crash, like this. You will be surprised how fast you run out of memory without using a garbage collector. And then you get an idea why garbage collection is so important. So that's a quite interesting one. Shenandoah, who knows that one or heard of it? This was done by Red Hat, more or less from Roman Kenke, and I think some or two other guys worked on that mainly. That's at the moment the only non-generational garbage collector in the JVM. With JDK 24, there will be an experimental version of a generational Shenandoah collector. That means it will be even faster. Why will it be faster? Because if I don't have a generational collector, that means every time I run out of memory, I have to do garbage collection on the whole memory, right? When I do have generations, I can do young generation garbage collection, old generation garbage collection. That's the advantage that brings me performance. But still, this one is quite fast. I think they guarantee around 15 milliseconds max garbage collection pause with the non-generational one, but usually it's around 1 to 2 milliseconds, so it's quite fast. They use the Brooks pointer. They use also a new barrier principle. You see the overhead increases again now to 10 to 20%. And this is made for very large heaps, right? So all the collectors that I show you now, it's 2 more coming. They are let's say they love cores, right? If you have 40 cores, great. If you have 80, even better, right? 120 gigabytes of RAM are nice, but if you have 512, cool, right? So this is the stuff that is used by Netflix, right? This is the kind of machines we talk about, like more than 100 cores and I don't know how much heap, but huge. And in this environment, these collectors are great because they are made for this, right? So you can use them on a Raspberry Pi, they will work, but they will be terrible, but it will work, right? So this is stuff that is made for huge machines, like heaps of 100 gigabyte plus. Yeah, it's not available in Oracle JDK. I'm not really surprised because it was not developed by Oracle, so they say no, we don't care. But it is an Oracle Open JDK, right, which is a different thing. Yeah, you have a little bit reduced throughput because of the concurrent GC. It uses barrier concepts like write barriers they use and the Brooks pointer. And like I said, JDK 24 will give us a generational version of Shenandoah, which seems to be quite fast, like in the same range as the ZGC. And there we go, ZGC, the Z garbage collector. Who heard about it? It's the newest one in the JDK. Again, a region-based collector, as Shenandoah was too. And we have only 2 generations. We have old and young, right? Or young and old. So it means if some objects are old enough, they will be promoted into the old generation. That means you can do a lot of garbage collections in the young generation and just a couple of times in the old generation, which brings you performance. I won't go into detail on this one, and there's a reason for that, because this is more or less a copy of the next one. It came with JDK 15 as the non-generational version, and then with JDK 21 we got the generational version, and in the meantime the non-generational is deprecated, so it will go away because it's slower. There's no reason to keep it. It's fully concurrent, it's fully parallel, it's made for large heap sizes, and it can be in the terabyte range heap, right? What else? High throughput, short pause times. I think it's always around 1 millisecond and even less than 1 millisecond. That means this is more or less a pauseless garbage collector. As mentioned, you need a powerful machine to really make use of this. Right? You can use it on your machine, it will work, right? It's no problem. You probably won't see a difference to G1 if you use a desktop application. Even in your microservice, you won't really see a big difference. But if you have huge applications with big heaps and lots of performance needed, then this collector is quite good. Yeah, non-generational will be deprecated. So, and now that leads me to the last one, which is made by Azul, of course. But we did that already more than 14 years ago. And this is the same as ZGC. Right? So ZGC is really a copy of this collector. The same algorithm, they just give it different names. They have one difference in the generational version. Everything else is the same. So everything that I tell you now also applies for ZGC. That means, yeah, we only have it in our own Zing JVM. There's also a reason for that. We use a so-called loaded value barrier. This is a read-write barrier. And if you look up ZGC, they name it colored pointer. But it's exactly the same. It's in the object header. We store some additional information. And yeah, like I said, it's a read and write barrier. It's 2 CPU instructions, which is probably the same in ZGC. And because it only runs on Linux, you should use THP, so transparent huge pages, to make the regions bigger. That also applies for ZGC on Linux. I would just like to show you 2 things. The marking phase, because that's a little bit different. Like I said, same for ZGC. We have garbage collection threads. They start from the roots, right, from the stack frames. And we have always the LVB or colored pointer in ZGC installed. So what happens is the garbage collector thread goes through the heap follows all the references and marks them as live. And now the application thread steps in and allocates memory. And now comes a big difference, because the loaded value barrier, what it does, the code that is behind it, it realizes this is an empty cell, right? And whoever triggered it, we will mark this cell as live by the application thread, not by the garbage collector. That means with the next garbage collection step for the cleanup, this one will not be cleaned because it's already marked. And the garbage collector doesn't have to mark it. And that's the big difference here. So that means the application thread and the garbage collection threads work more or less together by using the loaded value barrier or the colored pointer. So we do the two instructions, it's test and jump. And then it will be marked, and then this information will be passed to the garbage collector so that it knows, okay, there is another live cell. So it doesn't have to do the job on its own, which is quite useful here. And as I said, same in ZGC. That means we don't need to do this remarking phase, right? So it's not needed in this case. And then we come to quick release, which is another feature. I'm not sure if this is in ZGC. I bet it is. If we have the regions here and we do a compaction, that means we copy them into new regions. Then we have virtual memory here, but we also have physical memory, right? This is the one that we use. And there's something called memory paging that's done by the operating system usually. And this is one of the reasons why we only run on Linux with this one, because we tweaked the memory access from the operating system to the physical memory and made it, and this is no joke, 1,000,000 times faster. And that's the reason why we have it only on Linux, because that doesn't work on Mac and Windows. So what we do, we copy the objects from the old location to the new one, right? We move it to this. And then what we do, instead of installing the information where the new object is in the old object, we just put it off heap in a page. And ZGC does exactly the same. So that means this object is really just the old one. Remember, we had this forwarding header in the old object, and when we update all the references, we have to first update all references, and then we can remove the old object, right? Because it contains the information where to find the new one. Here, the information is stored off heap. That means we copy the next object, and now this area, this region, is more or less empty, right? Because we copied the live objects from there, and then we can just directly reuse the physical memory because we do the quick release. We know this information where the new objects is now stored here. We don't really need the old objects anymore. Okay, so we do the same stuff with the other ones, and then suddenly the application thread comes and says, oh, I have just the old reference. I follow the reference to the old object. It's not there anymore. It triggers the loaded value barrier. And this does the two CPU instructions like test and jump. It tests, can't reach it. It jumps to this location and gets the new updated position. And then it finds it here. And it updates this for all other objects too. So that means the next time someone tried to reach this one, it will directly go here, right? And this is done by the application thread, not by the garbage collector. Yeah.
Question: if we reference the same object via this concept, for example, with a string pool, which is from different stack frames, how would it update?
With a string pool, I don't know how this works.
Okay.
Because we had the same question during the other session, I have to look it up how that works with the garbage collector. But this is just an additional step. There is another thread going in parallel or concurrently that updates automatically all the references that are in this area at the same time. This is just if you reach an old one, the loaded value barrier will do that for you. So that means it's self-healing. So there's no need that the garbage collector has to update all the references, right?
So the element B that is triggered from one application thread
Exactly.
is not triggering the other application thread, but there is a separate thread that updates everything. Okay, gotcha.
So that's quite, and ZGC does exactly the same. So they do it the same way. Yeah, and like I said, this is only available in Zing, which is our own JVM, which is compatible to OpenJDK. Interesting part is the customer, we have one customer that has a huge heap, which is 21 terabyte. And it still pauses garbage collection, right? But you can imagine the machine. If it has 21 terabyte, it doesn't have one core, right? It's huge. But if you have this hardware available, these garbage collectors are really good, right? You don't want to use G1, it doesn't even work with these heap sizes. But these collectors are made for large heaps. So you have to keep that in mind when you create your application. How big is your heap, and then use the right garbage collector for that, right? Just because Netflix said, oh, we switched everything to ZGC, it's great. It doesn't mean it's great for you. Right? This is something you have to keep in mind. So this is how C4 works, not really important. This is the big question, which one to choose, right? We have 3 different criteria: throughput, latency, resource usage. And the good thing is you can only choose 2 of the 3, because it's the triangle of, I don't know, terror. If you would like to use very low latency and you need the highest throughput, awesome, but the resource usage will be terrible, right? You say, but I have restricted resources, but I need very low latency. Sorry, no very high throughput. This is the problem here, right? Again, doesn't really help you out of the box, so this is maybe better. I stole that from Roman Kenke because he did that in a JVM Summit presentation. It's pretty simple. If you don't care about pause times, right? But for you, resource usage is the biggest problem, then you're on the right side. Right? If you care about pause times and resources are no problem, you're on the left side. Everything else is in the middle. And this is usually where G1 is, which works quite good for most of the stuff. But there are use cases where you either use one of this one or the other one. It depends on your application, really. So there's no rule of thumb that says, oh, if you have this heap size, then you should use this. And it's really hard to figure that out. So you really have to measure your application and know how it works before you choose a garbage collector. Nevertheless, it's always a good idea to make some tests. If you think maybe we can be faster, give it a try. Why not? Overview. Probably more interesting if you have the slides, but this is more or less everything you saw on the slides in one slide, so you can compare and try to figure out where you are and what is the right collector for you. And with this, it's nearly 8:15, right? Plus nearly 35 minutes. So if you have questions, I think we just open it up already, right? And then thanks for attending. Yeah.
Do you have any standard example of big heap applications? What could come to mind? I don't know.
Oh yeah, as I said,
Spark processing.
Exactly. Kafka, Cassandra. If you use this in a huge way, then this is typically where we see the.
Okay.
And for example, this is something I didn't mention yet because of time. I told you that we see this drop in performance, right? This is the reason why in this JVM that we created, the Zing one, we have also a different compiler to keep up with this problem, right? The compiler produces faster code, so we again are faster than OpenJDK, which is still a benefit. And this is specifically for this big application. Like if you have a big Kafka cluster, then Zing really makes sense. You can see up to 40% performance increase just by changing the JVM. Where the garbage collection alone is ZGC or C4 is more or less the same performance. That doesn't make a big difference. But this is, again, big applications. This is where it shines.
Do you have any slides with a performance boost for Cassandra, Kafka?
We have, yeah. I don't have them here, but our salespeople have them,
okay,
probably,
cool.
because this is what they sell. But I know that we have, for example, Walmart is a customer, Netflix is a customer. They use Zing because of this performance boost. Especially for Kafka and Cassandra, we see up to 47%. Okay. This is mainly because of the garbage collector plus the compiler. We don't know exactly why the compiler is so good with Kafka and Cassandra, but it seems that the code that Kafka and Cassandra produces is very good for our compiler. So it really is faster with this one. Okay. Anything else?
I have 2 questions. First question is, how do you use such a garbage collector if it's not included already in the Oracle JVM?
Which one? The Shenandoah?
Yeah,
oh.
Whatever third-party garbage collector.
Oh, it's only Shenandoah that is not in the OpenJDK distribution from Oracle. Yeah. That means it's a little bit tricky, right? We have Oracle OpenJDK, And all the distributions take this code and build it, even Oracle. But in their own Oracle JDK, they remove Shenandoah because they can. This is the reason. There's
so
no
you
reason.
install then from some other distribution, from OpenJDK or so?
I have a session about this topic because it's quite complex. It's OpenJDK is just the source code. If you have Corretto from Amazon, Tamarin, Zulu from Azul, it's all the same.
It's all the same.
Yeah.
So you have to build your own JVM essentially from the source code.
You
That's what
can,
you're
but you
saying.
don't have to. So you can use a distribution, right? Like ours. We do that for you. Because there are other things involved here. Because to make sure that, for example, Corretto from Amazon, they add some stuff that makes it for them useful in AWS. This is not useful if you use it in, let's say, Microsoft, what is the name? Azure. They add other stuff for their own JDK. But still, they have to make sure that the code that runs on AWS in Corretto also should work on Microsoft JDK. That leads me to the TCK, right? This is, it's you see it. We go into a different topic here.
Yeah. And the second question is, how does all this compare if you would compile your Java code directly, like for GraalVM or something?
This is then not Java code anymore. This is totally unrelated. They also have a garbage collector. They can now, in the latest version, support G1. Before that, what was the other one? I think Parallel? I'm not sure. But what they do, they compile Java down to binary code, right? Yeah. Which is not Java code anymore. So that means all this doesn't really apply, right? Because it's different story. It's a binary that doesn't change anymore at runtime. Right, so it's like you get the executable file. There's no just-in-time compilation anymore. So you don't have to. You can't because there is no changings during the runtime. They have a garbage collector, but this is not the same as it would work in OpenJDK. It's different.
And performance-wise, can you compare to any of those?
I would always say the JVM still is faster, and the reason for that is that if you do. It depends on the application, definitely. Yeah. If you use GraalVM for small microservice, it's great, right? Because it's really fast and has a fast startup. The problem is if you have a bigger application, let's say you have an application server, which is, even if Netflix invents microservices, application servers are still out there and they are good. That means it's a big application that changes a lot of code at runtime. And the JVM can, through the JIT compiler, the just-in-time compiler, at runtime optimize the code, which you can't do with GraalVM because they can just do upfront compilation. And the problem with GraalVM is, yes, you can get GraalVM for free, but they're a little bit cheating. It's the same with Oracle Java. You can use it for free for 3 years, and then you have to pay because then they change the license. Or you switch to the next GraalVM version. That's good if you're a private person. If you're a big company, this is a hassle to change JDKs because it's not so easy. And this is why they try that, right? They try to, you take it for free, use it for 3 years, and then we give you the new update, which is then suddenly you have to pay for all your employees. You can use the completely free version, but this is not so powerful because then they don't give you all the features. This is a little bit the problem with GraalVM. And to be honest, they are not really a big few. I think they just have a few big customers. They really use GraalVM in production. It's some people, like mid-sized companies, they try it. But because I'm in touch with the people from the team, they told me they have one customer, paying customer for GraalVM. All the others don't pay. They are lucky that they use it because it's still not so easy to use, especially in bigger applications. Like I said, small services are great because then you don't have a lot of dependencies. It's easy. As soon as you get bigger with the dependencies, then not so easy anymore. So that's the tricky part. Performance-wise, I would say they're on par. There are examples where the JVM is faster. There are examples where GraalVM is faster. They have a good compiler, especially the former Enterprise Edition is good. But like I said, this is not for free, only for 3 years. If you use the Community Edition, it doesn't have all these features. It has the slower compiler. It doesn't have the, what's the name for it? Because when you do GraalVM, you can, Profile Guided Optimization, PGO. So they have in the Enterprise Edition, what you can do, you use the code, you run it in the JVM mode, you profile it, and then you take the profile and create a native image. This is only available in the Enterprise version. This is fast. In the community version, you can't use it. So that means the compiler has to guess. I think this method will be called like this, so I will optimize it. Oh, I'm wrong. My fault. This is the problem with the community edition. It's not that fast because it doesn't have all the features of the Enterprise version. I hope that answers this more.
Which kind of applications create only very little to no, or very little amount of objects by its nature?
Oh, this is not a kind of application. You have to create an application for that that fits to your needs. But there is a company in the UK, and I always forget the name. They have high-performance collections. And what they do, they are specialized to don't create any garbage. And it sounds easy. It's so hard to do that. They reuse most of the objects. They create them once, and then they reuse them everywhere. So, which leads to very terrible code, but it's blazingly fast because, and they work in the high-speed trading industry because this is where it's needed. And they use, for example, Epsilon as the garbage collector for their applications because they can, because they know how to do it, but it's really tricky. So I always forget the name, I don't know. It's a quite famous guy who's working there. Also Java champion, I always forget it. But it's a UK company, I know that. Yeah, but there's no easy way to do that. And if you take a look at their examples, it's like, you look at it and say, oh, this is Java code. Looks really weird. But it's really fast because they know exactly how it works.
This is why I said by its nature. So maybe there are use cases where it's not, where it doesn't feel strange to not produce much objects, so that it happens by nature somehow.
Oh, that's a good question.
Everything static methods and problem that there is no only objects from the view. There's a book about that in our Attendees section. You might be completely
Ciao.
It feels like a little Java with the front programming language German for it.
Yeah, exactly. So it's, you can do it, but like I said, if you take a look at the code, it looks terrible. So it's, yeah, you can use it if you like, but I wouldn't really do it. It's